As shown in the picture below, a box with mass m is sitting on a slope that has an angle theta with the horizontal. The whole system is inside an elevator that has an upward acceleration a. What is the normal force and static friction on the box? So, first let's establish a reference system. So, for mine, I'm going to be saying that the positive x direction is going to be the direction parallel to the slope going in the upward direction. And the positive y direction is going to be the direction perpendicular to the surface of the slope. Now, based on that, I'm going to draw a free body diagram for the box. So, if this is the slope, here's the right angle, there's theta, and this is the box, then we're going to have the normal force pointing out in the positive y direction. You're going to have the force of gravity pointing straight down. And we can actually decompose this gravity into two individual vectors, or individual components. So this is the angle theta, because these two angles are congruent. So this one is theta, and that's a right angle. So this force becomes mg sine theta. From trigonometry, sine is opposite over hypotenuse. And this direction, the force going perpendicular to the surface of the incline, opposing the normal force, is mg cosine theta. So those are our two these are our two components of gravity. And we also have the static friction that's opposing this force of gravity parallel to the incline. And yeah, that's just the static force, or force of static friction. It's given to us in the problem since we're supposed to calculate it. And I don't have enough room here, but we're going to have an acceleration a. But before we start to solve the problem, if we draw this again with the box here and like all of the forces acting on the box and stuff, we can also decompose a into a component, into its component parts. So initially, a is going to be going in the upward direction, but we can decompose in the acceleration into the component perpendicular to the surface of the incline and the component parallel to the surface of the incline. And again, this is angle theta because the perpendicular and parallel components make a right angle, and this angle is congruent to this angle. So this is angle theta. So from trigonometry again, the perpendicular component becomes a cosine theta, and the parallel component becomes a sine theta. And that is how we can decompose a. I'm trying to draw theta here. Also note that you can set your reference frames to be directly pointing up, directly up for positive y and directly sideways for positive x. But if you were to do this, you would instead need to decompose the normal force and the force of static friction into their components. So it doesn't matter which reference frame you use, as long as you decompose the necessary components, or the necessary vectors into their component forms. So from here, we can apply Newton's laws to solve this. So Newton's second law says that the summation of the net force, or the summation of all the forces, is equal to the object's mass times the acceleration. In this case, the acceleration is the acceleration of the whole system. So there is going to be an acceleration, because there is both an acceleration in the parallel to the surface of the incline and an acceleration perpendicular to the surface of the incline. So let's start with the normal force in the positive y direction. So the normal force minus the component of gravity perpendicular to the surface, mg cosine theta, so mg cosine theta, is equal to the mass times the acceleration. And this acceleration will be the acceleration perpendicular to the inclined surface. So ma cosine theta. A cosine theta. So now we just need to solve for the normal force. So we can move this over. Normal force equal to ma cosine theta plus mg cosine theta. So we can factor m and cosine out to get that the normal force is equal to the mass times the cosine of the angle theta times the acceleration plus g, where g is the gravitational acceleration. And that is our expression for the normal force. So I'm going to rewrite that. The normal force is equal to m cosine theta times a plus g. And that's the first part of our problem. Now it also asks us for the force of static friction on the box. So now we can use the same thing, but we can apply it in the direction, in the x direction, parallel to the incline, surface of the incline. So the force of static friction, which is going the positive x direction, minus the force of gravity in the x direction, mg sine theta, is equal to the mass times the acceleration. And this is the acceleration in the x direction. So this is a sine theta. And so the force of static friction is equal to ma sine theta plus mg sine theta, which, just like before, we can factor this out. Say that the force of static friction is equal to the mass times the sine of the angle theta times the acceleration plus the gravitational acceleration. That's the force of static friction. And this is how you would solve this problem here.